Good morning, student. Today we are going to see that synthesis of acetoacetic ester, that is ethyl acetoacetate. This is the structure of ethyl acetoacetate. This compound is basically synthesized by Cleanzen condensation reaction. What is Cleanzen condensation reaction? When a ester molecule having alpha hydrogen atom. What is alpha hydrogen atom? A hydrogen atom which is present on alpha carbon atom. So condensation reaction of ester having alpha hydrogen in presence of base, sodium ethoxide here is base, to form beta diketone is called Cleanzen condensation. So just here see why this acetoacetic ester is beta diketone. So in this case both the carbonyl group are from beta position to each other. Next to this carbonyl, this carbon is alpha and this carbon is beta. So this carbonyl group is at beta position from this carbonyl group. Same way this carbonyl group is from beta position from this carbonyl. So this class of compound is also known as beta diketone compound also. So just see here mechanism of Cleanzen condensation. In a first step, one of the molecule of ethyl acetate is taken. So during when this ethyl acetate is a reflux with your mild base, that is sodium ethoxide, one of the hydrogen, that is alpha hydrogen, is taken away by sodium ethoxide and C2H5OH basically goes away in the reaction, and this carbon, that's why got negative charge, because this proton is removed by a base. So your carbon got negative charge. That is basically a formation of carbon ion is taking place here. Any species having negative charge is basically known as nucleophile. So this nucleophile in next step attack on carbonyl carbon of other ethyl acetate molecule. So just see here, this negative charge basically attack on your carbonyl carbon. Because of that the double bond is shifted here. So this molecule attached to your this carbon, which is shown by red color pen. So when a negative charge goes on this oxygen, so Na from your ethyl acetate stabilize or comes here. So we got basically a structure CH3 CO negative Na plus O C2H5. Always remember part of the molecule which is written by a blue pen, it is come from your first molecule of ethyl acetate, while the second part which is written by a red pen, it basically comes from second molecule of ethyl acetate. When this molecule is formed, so bond between one of the carbon and hydrogen shifts here. Because of that this C2H5O, this bond is shifted on the oxygen, and C2H5OH goes away because oxygen negative, this hydrogen then comes as a positive, C2H5OH goes away, that is ethyl alcohol goes away during this reaction. So this carbon and this carbon forms a double bond. So just see here, CH3CO negative Na plus double bond CH, C double bond O, OC2H5. Remember that this portion comes from second molecule of your ethyl acetate, red color side portion. When this molecule undergo acidic hydrolysis, so this Na is basically replaced by hydrogen. So hydrogen is replaced here. So just see this molecule, it is alkene double bond, that's why it is in here, and this carbon having OH, so it is OL also, that is alcoholic OH. So this is basically what? Enol form, a compound in which a carbon is attached with double bond with adjacent carbon, and that carbon having OH functionality, that is known as generally enol compound. So since it is a enol compound, we can easily write its keto form, or it undergoes ketoenol tautomerism. How? Just shift the hydrogen which is on your oxygen. So this bond shifted here, so it's converted into C double bond O. So this bond goes on your this carbon, so this carbon is negative, so it takes this hydrogen on itself. So CH3, C double bond O, CH2, C double bond O, OC2H5. It is the keto form of this enol form, and the phenomena which is goes here, it is known as tautomerism. And in this way we got acetoacetic ester, that is keto form of your this compound. Now what is tautomerism? The phenomena in which isomers forms having different functional group. It is important. Just see here, both these two compounds are isomers of each other and both having different functionality. This carbon having here keto, it's having OH, are spontaneously interconvertible. Both this compound can interconvertible to each other by just shifting a bond of hydroxyl group, and exist in dynamic equilibrium. They are always in dynamic equilibrium, is called tautomerism. Generally, keto at a room temperature, your acetoacetic ester is a mixture of 92.5% of keto form and 7.5% of enol form. So now we are going to see some of the properties of ketonic group or chemical reactions of ketonic group. So just see here, acetoacetic molecule have two carbonyl group. One is shown by red pen, another one is shown by blue pen. But the group which is shown by blue pen, it is basically a part of ester group. So if we add HCN, so addition type of reaction is taking place on your first carbonyl group. It is important. So we got cyanohydrin. Basically this bond shifts here, CN attack here, and H is gone on your oxygen atom. When we add hydroxylamine to first carbonyl group which is shown by red pen, so 2 of hydrogen of your hydroxylamine reacted with your this oxygen, or they takes away that oxygen, condensation reaction goes here, and NOH attach here. Reduction is also can also be taken on your this carbonyl group, that is first carbonyl group. If we add mild reagent just like sodium amalgam, so due to reduction of keto group, hydroxyl group can easily form. One of the hydrogen goes on your oxygen, other comes on your this carbon. Basically this double bond is breaks away during reduction. So we got ester of beta hydroxyl butyric acid. So it is ester of beta hydroxyl butyric acid. Now what happens when we treat this compound with aqueous KOH and alcoholic KOH? These reactions are very much important. They are the part of multi-step synthesis. So it is the important reaction. Students should take note of that. So when we add aqueous KOH, what going to be happen? The second carbonyl group, that is here, which is the part of your ester group, when we add aqueous KOH, so you can take help of water here because KOH is dissolved in a water. So decarboxylation reaction taking place means the carbonyl group, which is the part of ester group, this carbonyl group takes one of the oxygen from your water molecule and CO2 molecule goes out. One of the hydrogen is taken by this C2H5O and hydrogen comes from water. So alcohol, ethyl alcohol is also comes in a byproduct. One of the hydrogen of water attach to your CH3 C double bond O CH2. So we got basically a acetone. So when we add aqueous KOH in ethyl acetate, so generally keto molecule is formed. It is important, generally ketones are formed. Now if we add alcoholic KOH, so just see here in your product what we got here acetic acid. So here is acid and C2H5OH goes away. So what is the important things in this two reaction which we have to know? When we add KOH, decarboxylation of your compound taking place and ketone is a main product, while when we add KOH alcoholic, that is concentrated KOH, also main product which is formed is acid. So now we are going to see properties of enol group. Since we know that this compound undergo keto-enol tautomerism, so we can, this compound is also going to give some of the chemical reaction of your alcoholic OH. If we add sodium or sodium hydroxide in this molecule, so this hydrogen, which is the part of your hydroxyl group, is replaced by Na, and if we add NaOH, so Na is replaced here, water is goes as a byproduct, or if we simply take sodium, this H is replaced by Na, which is shown here. So what we got basically sodium salt of acetoacetic ester. If we take acetyl chloride, that is CH3 C double bond O Cl, so this Cl takes away this hydrogen, so HCl goes away and whole this part of molecule joined to your oxygen atom. So it is known as orthoacetyl ethyl acetate. This is basically a acetyl functionality. It is known as O-acetyl ethyl acetate. If we add bromine in this compound, what going to be happen? This double bond breaks away and addition reaction goes on. So both the bromine add, one of the bromine add on this carbon, other is add on this carbon. So we got dibromo derivative. So this is the most important part of your chapter, that is synthetic application of acetoacetic ester. So just see here, this methylene group in acetoacetic ester comes in between these two carbonyl group. So it is basically a active methylene group. What going to be happen when active methylene group is treated with a mild base? One of the hydrogen goes off. So if we take mild base C2H5ONa, that is sodium ethoxide, one of the hydrogen is replaced by sodium, that is Na. If we add again sodium ethoxide, so second hydrogen can also be replaced with sodium. So it is disodio-ethyl acetoacetate. So now we are going to see how acetoacetic ester is used for the synthesis of straight chain monocarboxylic acid as well as branch chain monocarboxylic acid. So just see this reaction sequence. Before going deep into this sequence, please note that from your this molecule, which is I denoted with capital A, two reaction route can be drawn. Two reaction route can be possible, which give two different acids molecule or different types of acids. So just see what we want to say. If we take acetoacetic ester and when it is treated with sodium ethoxide, one of the hydrogen is simply replaced by Na because it is active methylene group. And if we add alkyl halide, so Na is basically replaced by R, minus NaX goes off from this reaction and we got this type of compound. So now what happen if I add concentrated KOH in this molecule? So basically we are going to see the root 1 of your reaction sequence. If we add KOH in this molecule, and it is, since it is a concentrated KOH, so we see in our first reactions, that is in the reaction of ketonic group, if we add concentrated KOH, acid is formed. So acid is formed. How this acid is formed? That is RCH2 C double bond OH. So when we add concentrated KOH, basically two molecule of water can be used to write the product. So one of the molecule of water we can write in this way. So MECH double bond OH, that is one of the molecule of acetic acid is formed, and it ETO and this H gives you ethyl alcohol, while this carbon takes one of the hydrogen from this water molecule and this carbon take OH from your water molecule. So what we comes with RCH2 C double bond OH. So in this overall this reaction route number 1, what is the important thing? Just see here, this R is basically coming from your reagent, while this part CH2COH, it is basically coming from your malonic ester from this side. Now if we add C2,5-ONA, that is ethyl sodium ethoxide, so another hydrogen can be replaced by Na, and if we again add alkyl halide, so this Na is also replaced by R dash. Again if we add concentrated KOH, so same thing is going to be happen. That is, we got acid here, that is C, that is R C R dash CH COOH, one of the molecule of acetic acid, and ethyl alcohol goes away. Now important thing during this whole reaction sequence, that is from your route 1 and route 2, what we want to say, if we want to prepare monocarboxylic acid, straight chain monocarboxylic acid, so in your this molecule we directly add concentrated KOH. But if we want to synthesize branch carboxylic acid, branch monocarboxylic acid, so we have to again repeat this reaction sequence. That is, we have to take C2H5ONA again, then we again add alkyl halide, and then the concentrated KOH is added. Now in overall both the two route, what we are going to see, so these are in your reaction route 2, and R dash is basically coming from your reagent in the place of your active hydrogen of acetoacetic ester, and this portion, that is CH-COOH, it is basically a part of your acetoacetic ester, and R dash is basically a part of coming from your reagent which is added during reaction sequence. If R is equal to methyl in route number first, if R is equal to methyl, so this R is replaced by methyl, so we got propanoic acid. If R is replaced by C2H5, we got butanoic acid. If R is replaced by propyl group, that is C3H7, we got envaleric acid. It is important. Now just see here, if your R in your step number 1, if R is replaced by CH2 C double bond OOET, if R is replaced by CH2 C double bond O OET. That is, if this compound is ester of chloroacetic acid, then we got succinic acid, that is, it is the dicarboxylic acid. In a root number 2, if R and R dash is same, that is, in step number 1 we add methyl chloride, and also in step number 2 if we add methyl chloride, so we got dimethyl acetic acid. If in your step number 1 we add methyl chloride, and in your step number 2 if we add ethyl chloride, or vice versa, we got product 2-methyl butanoic acid. In our next class, we are going to see some more application of acetoacetic ester.